Okay, so just since you are recording, welcome to second part of this session on electric vehicle and modeling. And I already explained introductory part, like my personal introduction outline. So I want to skip all these from slides like award, membership, website, teaching award, Waterloo Institute of Sustainable Energy, then reputed publications, then Google Scholar, then reviewer, then about Waterloo, and this is the video for University of Waterloo. So I think I was here, Sagar. Okay, Sagar, am I audible?
Yes, sir. Yes, sir.
Perfect. I think this video is not able to play, so I don't want to. I don't know. Let us keep this part. I'm fine with this, and you guys can see this later on. Okay. Again, uh, again, I'm looking for two master student or one PhD student. Okay, and again for PhD, it is typical 5-year funded program, and but again, if you are coming for masters and if you want to switch directly into PhD, that is possible now. It is called integrated degree, and I can do that one also if you are a good student. Okay, fundamentals of EV. Let me, in first part, I skip this one. So what is the primary and secondary cell? So primary cell is typically a cell in which irreversible chemical reaction generates electricity, and a cell that cannot be recharged basically. And the secondary cell is basically a cell which we can charge and discharge. So basically it is a rechargeable electrical cell that converts chemical energy into electrical energy by reversible chemical reaction. So typical examples of primary battery cells which you can see over here. So like let's say the Duracell. So examples are the Duracell or Energizer or alkaline zinc manganese or zinc carbon or lithium metal and zinc air. And secondary battery is basically typical examples are 12 volt lead acid battery where we use for a start and stop of the vehicle. Then lithium ion battery, we can charge number of means charge discharge cycles. Then nickel metal hydride, nickel cadmium battery. Then the reverse battery is the battery which is inert until operation is performed to bring all components into the proper state, means state of charge, and location becomes active. So examples are missile or life-based batteries. Cell module and pack. So as I explained in my previous one about the cell experiment, so cell is the smallest part which has a voltage window of around 6 volt, and when number of cells are connected in a series or in a parallel, which you can see over here, and that contains the battery pack, sorry, module. And this type of module are connected in a pack. So one module, second, third, four, five, six, which builds the battery pack. So module is basically a series of several cells generally connected either in series or in a parallel. And battery pack you can see over here, or this is the Tesla, probably the cylindrical cell one. Battery pack is the assembly by connecting module together, again either in series or in a parallel. Yeah, couple of units. Battery voltage is basically, we all know, is the measure of energy per unit charge. Current is measured in ampere. Capacity is measured in amp hour of the battery. So total electrical range. SOC probably you know is called the state of charge. So that is percentage of measure of charge remaining in the battery related to its predefined full or empty state. So full means the 100% SOC and empty means 0% SOC. Depth of discharge, DOD, is opposite to the state of charge. So basically, let's say if your battery is at 60% state of charge, the opposite is 40%. That is called the depth of discharge. And SOC, so just to give an idea, state of charge is SOC is the how much gas is there in the tank if you compare with gasoline vehicle or petrol vehicle, and DOD is the how much gas is or how much petrol is removed from the tank. C rate and the E rate. So C rate is basically the charge and discharge current of the battery that is measured in the C rate, and majority of small batteries are rated at 1C, and which is, let's say, 100 amp hour battery. 1 sim is 100 ampere constant current discharge. In my previous stuff, I explained 20 amp hour battery. So 20 amp hour means 1 sim is 20 ampere constant current discharge, 2 sim is 40 ampere, 3 sim is 60, and all the way like that one. And E rate is the discharge power to the discharge battery entirely in 60 minutes. And next one is the power. We all know is measured in watt or kilowatt, that is voltage into current. Energy is watt hour, so basically C amp hour, and then the voltage of the battery. Energy density is measured in watt hour per liter. Specific energy is measured in watt hour per kg. Power density is measured in watt per liter, and specific power is measured in watt per kilogram. Couple of other common units related to electric vehicle are state of health. So if you know the SOH, so basically it is a measure of battery condition compared to its initial or the ideal state, measured in percentage. So it is typically measured at BOL called beginning of life, even MOL called middle of life, and EOL called the end of life of the battery. That this term is probably new term. If you are in electrical, you might know, but if you are in mechanical or chemical, so open circuit voltage known as the OCV or VOC is the voltage when there is no current flow on the battery, or typically very marginal current of, let's say, 0.5 ampere or the 1 ampere current flow on the battery, and it is subsequently basically no chemical reaction occur within the battery, and that voltage is known as the open circuit voltage. Terminal voltage is the voltage between terminals of the battery. So basically the 3.6 and the 2 volt. So voltage window. Nominal voltage is the voltage, reference voltage or reported voltage or supplier provided voltage, and typical nominal voltage for all batteries are around 3.6 volt. Of voltage is the voltage, so minimum voltage basically during the discharge curve of the battery. So this minimum voltage 2.0 is known as the cutoff voltage. Then charge voltage is the voltage to which battery is fully charged. So after discharge, you fully charge the battery up to this voltage, and that voltage is known as the charge voltage of the battery. Float voltage is the new term, that is the voltage at which the battery is maintained after being charged to 100%. SOC maintain that capacity by compensating for the self-discharge of the battery. Now, why lithium-ion battery? I did not explain in previous presentation, but just a couple of typical parameter or typical components for the battery are cathode, anode, then the separator, and during discharging, current flow from like the anode to cathode, cathode to anode, electron travel from anode to cathode, and lithium-ion travel via separator sheet. If you look at this table, it gives the comparison of lead acid battery versus nickel metal hydride versus lithium ion. So if you look at lithium ion battery, the nominal cell voltage is ranging from 2.5 to 3.7. So it has wide nominal cell voltage, while lead acid has only 2 voltage and nickel metal hydride has 1.2. Specific energy in watt hour per kg is also high, that is 19 to 220. The specific power in watt per kg is around 600 to 3400. Cycle life is extremely good. So you can charge and discharge this cell from 1000 to 8000 times. And this is why lithium ion battery is the most efficient battery used nowadays for small device like laptop, mobile, all the way to electric vehicle. And even temperature range is also very good for particular operation for this battery. But when it comes to the costing part, relatively high as compared to lead acid and the nickel metal hydride and couple of other batteries also. So that is why lithium ion battery is the most advanced battery technology nowadays used in all small to all the way to helicopter or electric vehicle also. Different types of batteries are coin batteries. Typically, we don't use for electric vehicle, but we use for wristwatch. So this is the coin battery. Second one is the cylindrical battery, and Tesla motor is using this cylindrical battery, that is 18650. So if you see this term 18650, so 18 millimeter is diameter and 65 millimeter is the height. If you look at the Tesla motor, they have 21700, so 21 millimeter diameter, so bigger diameter, and height is like the 700, so it's a very big cell basically. And same way, so that is second one is the cylindrical. Third battery is known as the prismatic battery, which you can see over here, where anode and cathode are located over here, or new batteries has positive and negative and opposite direction. So different types of batteries with different constructions are available in the market. Even nowadays, you can see this pouch type of battery also. Then cell operation, I don't want to go into detail, but these are the chemical reactions for positive electron, negative electron, and overall one. For chemical process, I already explained in my previous slide for P2D model, like the electrochemical model. And so these are the processes for electrochemical side. Cathode chemistry, I already explained in my previous slide. And typical three dominant chemistries are lithium cobalt, lithium manganese, and lithium phosphate. And anode materials are graphite and silicon, and separators are provided over here. With lithium salt is also LiPF6, so I think lithium perchlorate, and LiBF4, so lithium borate also. LG Chem process is already there. So just to give you an idea how the battery is manufactured. So since we have time, let me play this video if it works. It's only 1 minute video. I don't think it is going to work out. Forget about that one. Okay, I will provide this slide and you can see this one later on. Okay, so this is the production of the battery. And gasoline car, I have already explained. So due to gas price and sorry, due to increase in gas price, carbon concentration, then greenhouse gas emission, we need alternative for this one is called the battery, and heart of the for EV, and heart of EV is the battery, and problems with the battery are provided over here. Even BMS is the new part called the battery. BTMS is the battery thermal management, but BMS is also the new research area called the all cells. So let's say you have 300 batteries in this one. So all cells should give the enough voltage, and that is part. So cell to cell variation, so that is also another hot topic in industry. So first one is the thermal runaway, and I have a big project on that one. And second one is the BMS called the battery management system. So cell to cell variation, voltage variation, and SOC swing is also another hot topic right now. So by the way, we are also working on machine learning for the BMS side and algorithm development. So those who are in computer engineering, we also hire computer engineering students for the machine learning part, like the Python, C, C++. So those coding part basically. Again, this slide I did not explain in previous one. So it's a high. What is the difference between EV, HE, and PEV? So hybrid electric vehicle is the electric vehicle which has internal combustion engine as well as electric motor and the battery. And typical hybrid electric vehicles are series parallel or series parallel combination also. Here you can see the Audi e-tron motor, which has like the battery pack and then the internal combustion engine and the motor. And I will explain later on in my slides also. Second one is the PHEV, known as the plug-in hybrid electric vehicle. It is type of hybrid electric vehicle, but it has two different range or different ranges. So let's say PHEV 40 and PHEV 60. PHEV 40 means 40 mile, PHEV 60 means 60 miles, so around 80-85 kilometer, or let's say 100 kilometer. So if you want to drive only within Pune region, so you can use the PHEV 100, and let's say if you want to go outside to Pune, you can use the in the gasoline mode also or petrol mode also. So plug-in hybrid vehicle is the part of hybrid electric vehicle, but it has different ranges also. So depending on your requirement, you can design your PHEV. The third one is the full EV. Full EV means it has no internal combustion engine, so no IC engine, and only electric motor and the battery. And I will explain in the later stage of this presentation also. Now, very important part or very important topic of this presentation is the Transport Canada project. This project name is basically Battery Lifecycle Management for Ford Escape EV as well as the plug-in hybrid electric vehicle. It has four basic fundamental tasks. So when we received this project, big project from government, from Transport Canada, first one is the management of the vehicle and grid performance data. So to accomplish this task, 3 data logger have been installed in 3 different vehicles, which I will explain in later stage. 1 electric vehicle and 2 hybrid electric vehicle, and data has been collected over several months and data analysis was done. So first part is the data management and installation of the data logger in the vehicle. Second one is the modeling in of electric vehicle into the PCET or autonomy for degradation part. And for this model was built and validation. Third one is the fleet vehicle as well as the EV comparison. So two Ford Escape hybrid electric vehicle comparison with this electric vehicle performance under the same condition and comparison of those results basically. And fourth part is the analysis of current battery market and risk associated with the disposable part. So uh, okay, so the fourth one is basically like the secondary use of the battery actually. So first one is about the vehicle. So if you look at this vehicle, the first one is the blue color one, that is the pure electric vehicle, and it has like, so instead of engine here you can see the electric battery pack. Second, vehicle number 3 here you can see the hybrid electric vehicle. So remaining two whites are hybrid electric vehicle, and this type of data logger was installed in all three vehicles: electric vehicle 1, hybrid electric vehicle 1, and hybrid electric vehicle 2. And then data has been collected over several months for these particular three vehicles. Before I start, am I still there? Am I audible, guys?
Yes, sir. Yes, sir.
Okay.
Absolutely.
Are you able to see my screen change also?
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Yes, sir.
Sounds good. Yes, after typical, but so electric vehicle specifications are, so here you can see the first electric vehicle. So it's called Burlington Hydro because Burlington Hydro Company was part of this project. So REV called Rapid Electric Vehicle, second one Burlington Hydro, and third one University of Waterloo. So these three were partners for this project. So that is why it is called the Burlington Hydro EV. So first electric vehicle was electric vehicle 2, which you can see over here, and it has 90 kilowatt motor. But later we changed this motor from 90 kilowatt to 125 kilowatt hour, so bigger motor, and that is why it is called PCX 2.5. So it's basically newer version of this electric vehicle. So dimension, everything same, but only the motor is changed. So this new motor is UQM power phase 125 kilowatt, which you can see over here. It is placed below this battery pack. And so we took out the battery pack, and at the bottom of this battery pack, you can see this UQM 125 kilowatt motor. Even it is the first vehicle is ACX2, which has old charging port, and then we put this type of new charging port, and that is called the ACX 2.5. So basically same model, we did some modifications, and it is called EV2 and EV 2.5. For modeling, we need couple of parameters. Or vehicle mass is basically 2000 kg. Motor peak power is 125 kilowatt. Motor efficiency is 98% at 4000 RPM. Peak torque is 300 Newton meter. Battery module nominal voltage is 19.2 kilowatt, sorry, volt. Battery module energy density is 89 watt hour per kg. Battery module nominal capacity is 69 amp hour. And total capacity of this vehicle, means the battery pack, is around 25 kilowatt hour. So this vehicle has 3 battery pack, and I will explain those 3 battery pack later on. But total capacity of all 3 battery packs are 25 kilowatt hour, and typical range is 100 kilometer, and full means 100% SOC, and it takes around 12 seconds to reach from 0 to 100 kilometer per hour, and with the charging time of around 4 hours, so 3.89 hours. So these are typical vehicle parameters for this electric vehicle. If I continue with this next part, so as I said, it has 3. So this is something about the battery pack module as well as the cell specification. So this vehicle has 3 battery pack. First battery pack is at the front of the vehicle. Second battery pack is at the middle of the vehicle, and third battery pack is at the end of the vehicle. So here you can see somewhere like the third battery pack, and the first battery pack is over here. So if you open the first battery pack, you will see this type of image. So this first battery pack has 1, 2, 3, 4, 5, 6 modules. So one battery pack has 6 modules. Inside this module, this type of 18650 means cylindrical cells are there. So typically each module basically has 6 series multiplied by 49 parallel strings, that is equivalent to 294 cells multiplied by 20 module, which gives us around 6,000 cylindrical cells. So this vehicle has 25 kilowatt hour battery pack, 3 battery pack all together with 20 module, and 49 multiplied by 6 series with 18650 cells has almost 6,000 cylindrical cells. Now, cylindrical cells parameter, as I said earlier, 18650 means 18 millimeter diameter and 65 millimeter is the height. So number of battery pack 3, number of module, as I said, 20, number of cells 6 in a series, cell voltage typical 3.6, and operating voltage is 3.2, over capacity is 1.4, and discharge cutoff voltage is 2.5, and typical cell is around 50 gram. So one cell is around 40 to 50 gram, and length, and so as I said, 18 millimeter diameter and 65 millimeter is the height. After that, the motor parameter. So here you can see the UQM 125 power phase motor, and so installation of motor inside the vehicle, and typical picture for like a motor with the controller is provided at the bottom. So weight of the motor is around like the 41 kilogram, length and diameter are provided. Performance wise, 240 volt DC, 500 ampere motor speed, 8000 rpm, 300 newton meter torque. As I said earlier, maximum output power is 125 kilowatt because it has to match with this 125 kilowatt hour for the battery pack. 125 kilowatt, and that is the battery. So it has to match basically output power with the battery one. Maximum efficiency 94%, and a couple of other parameters for, if you compare ACX2 with ACX 2.5, as I said earlier. So previous one was previous vehicle had AC induction motor. Next one has AC permanent magnet motor, electric motor 90 kilowatt, and new one has 125 kilowatt. Torque Newton meter 239, newer version has 300 Newton meter. Range 80 kilometer, updated all the way to 140 kilometer. Charging time 5 hour, reduced to 3.89 hour, and transmission is single speed gearbox, and here with the electronic tackle lock. After about the specification, what we did is we installed this data logger. So the data logger is basically from the Isaac company. So we took the Isaac data logger, that is from the Montreal, that is in Quebec City, and we installed that in the vehicle. And here you can see the GPS called global positioning system, and here 12 volt shutdown wire is provided. So below the passenger seat, so here you can see the laptop, and below the laptop, so here like below dashboard, we have like the Isaac data logger and 12 volt shutdown wire. And now couple of important signals are battery voltage, so which monitor vehicle energy use and regenerative braking. Then we need the battery current also, which gives the energy use and regenerative braking part. Module 1 to module 20 temperature, module 1 to module 20 state of charge, motor voltage, motor current, motor speed, vehicle speed, motor torque, vehicle acceleration, accelerator pedal, and brake pedal position. So for driver demand also. So this is something about data logger and shutdown wire. And after that, after installing data logger in this electric vehicle, we draw the vehicle from Toronto. So here you can see the Toronto almost all the way to Burlington, all the way to Niagara Falls. So the vehicle was driven from Toronto to Niagara Falls on highway called QEW, called Queen Elizabeth Way. And that is one of the second busiest highway in Canada, connecting Toronto to Buffalo, means New York State. And so we drove that vehicle from like Toronto to Niagara Falls, including the city driving, stop and go means intersection, and then the highway driving also. So here you can see first, I think someone is speaking. I request everyone to mute yourself, please. So vehicle, you can see over here, the first Canadian electric vehicle that was on display in 2011, and the vehicle was driven in November month, where outside temperature was around +5 degrees C. Now, total trip duration from Toronto to Niagara Falls was like 136 minutes. So then so 2 hour and 16 minutes. Distance was 106 kilometer. Starting SOC was 100%, ending SOC 2%. As I said earlier, total amp hour capacity, sorry, kilowatt hour is 25 kilowatt. So total energy consumption was 25 kilowatt hour. Average speed was 46 kilometer per hour. I drove this vehicle, little scared at that time, but I drove the vehicle with a maximum speed of 125 kilometer per hour. Accelerated positive average is 0.59 meter per second square, and peak position is 3.43. Now, drive the vehicle from Toronto to Niagara Falls and then back, is charging around like $2.60, which is very affordable one, and cost per kilometer is around 0.024 Canadian dollar per kilometer. And as I said, in November month, temperature was plus 5 degree. By the way, right now the temperature is minus 23 degrees C over there. Okay. After installing data logger and collecting several trips, we did this energy and cost analysis of the vehicle. So if you look at this vehicle, we draw the vehicle. So Burlington Hydro Company and REV called Rapid Electric Vehicle, and this type of monthly reports were generated. So November, December, January, February, March, all the way for 1 year or 2 year. And it was found that total kilometer for this vehicle is around 308. Gas consumption 0 because it's pure electric vehicle. On hours 9.6, off hours 710, so idle hour and driving hour, and charging hour and resting hour. So here you can see charging and the resting. Driving energy was also collected 0 liter, then because it's pure electric vehicle, then 65.5 kilowatt hour, then charging kilowatt hour. So driving as well as charging energy, energy path and temperature recorded, and corresponding start of trip and end of trip with the charge remaining and the charge remaining are provided over here. So this type of monthly reports were generated, and we publish in Transport Canada report also in the government sector. So this is, so the first part was the like the installation of data logger and management of the vehicle. Second part was the data analysis and the cost analysis, which is ongoing right now, which you can see in this slide. Then after longest recorded trip, so the vehicle was driven from, as I said, Toronto to Niagara Falls, and that trip is around 8,000 something seconds, so 2 hour and 16 minutes. With maximum speed here you can see 125 kilometer per hour, and so vehicle speed versus time is provided over here. Corresponding battery current and the battery voltage is provided over here, and all 20 battery module temperatures are provided in this slide. And bottom right, you can see over here is the green color one. That one is the battery state of charge. So as you can see over here, starting SOC 100% all the way to ending SOC 0%. And battery maximum and minimum temperature are also provided over here. So this is something about a longest recorded drive cycle. Vehicle was driven for 2 hour and 16 minutes with 120 kilometer from Toronto to Niagara Falls. And then after that SOC was 0. So we went to one of the mall, and then we charged the vehicle, and then we came back. Now, energy and cost analysis was the second part. And here you can see this typical electric, first Canadian electric vehicle was driven in October, November, December, January, February, over 5 months. So distance travel, so say around 800 kilometer for this vehicle. Driving energy in kilowatt hour is around 179. Driving cost is around 19. So to drive the vehicle for 800 kilometer, the cost is only $19, means $20. So which is very affordable one. Charging energy on kilowatt hour is 222, and charging cost with, is around 24.48. So right now, let's say in India, I don't know, but if you charge the electric vehicle in Canada or North America between 8 p.m. to 7 a.m. or 8 p.m. to 8 a.m. in the morning, then your electricity cost is only 8 cents per kilowatt hour. So we have right now in Canada 8 cents per kilowatt hour. But if you charge the vehicle during daytime, then it is double. So around 16 cent per kilowatt hour. So your cost is almost double. So we have peak load, off load, and then the peak hours and then the off hours also. After that, energy and cost comparison was also done for this particular vehicle called the hybrid electric vehicle versus electric vehicle, and that you can see over here. So electric vehicle, so in November, December, January, February, so over 4 months, this hybrid electric vehicle was driven for 3,500 kilometer, and equivalent energy consumption from liter to kilowatt hour is around 2,000 something kilowatt hour, and economy means it's like 0.05 dollar per kilometer. If you look at the electric vehicle, it was driven for around 700 kilometer, and equivalent is over provided, and then 0.025 dollar per kilometer. So saving is around $94 for driving this electric vehicle as compared to this hybrid electric vehicle. So this was the second task for our Transport Canada project. So energy and cost analysis and the comparison. And third part is about the model development and the validation. So we use the PCET software. PCET is known as the Powertrain System Analysis Toolkit, and the upper version, so the latest version, is known as the autonomy. So either you use the PCET or the autonomy version for powertrain modeling. And this electric vehicle has typical components called battery, then motor, then torque coupling, differential, wheel, vehicle, and then DC-DC converter, and then electrical accessories. Here you can see the laptop and then the data connection, and then typical. So intake is the current. Here you can see the typical block is basically the state of charge calculations, then after the voltage calculation by Coulomb counting method, and the resistance part, and then thermal calculation by using the heat and then the temperature. So this is about the electrical. When it comes to this plug-in hybrid electric vehicle, this is little difficult to model for us because it has engine plus the battery part also. So typical starter, engine, then mechanical accessories, clutch, gearbox, final drive, vehicle, for wheel mass, then chassis, then high voltage battery means ESS called energy storage system, then the UQM power phase motor, power converter, and electrical accessories. After that, I said autonomy session or set is used. So typical input parameter is the vehicle speed or driver basically. So driver is the input, and then we have several blocks or block diagram tip. It's a long detailed model, but so typical vehicle speed versus time is the input, and then it has the driver and then the powertrain, like the state of charge and the drivetrain, and here the brake, and then couple of other parameters are also provided in this one. After more, you need almost 400 parameters when it comes to this electric vehicle. So typical important part is, as I said earlier, heart is the battery, means energy storage system, and typical parameters we need like the number of cells either in series or in parallel, then initial SOC, like nominal cell voltage, then minimum allowable cell voltage, maximum allowable cell voltage, then pack SOC, then module diameter, module length, module surface, then case thickness. So those typical Coulomb efficiency, internal cell resistance during charge as well as during discharge, nominal discharge, thermal resistance. We need all those parameters for this energy storage beyond. Second important part is about the motor, which you can see over here. And for that, we need the motor inertia, then the constant, then motor mass, motor controller, base speed, motor speed, maximum, minimum speed, torque index, two-quarter speed, whether 2-speed, 4-speed, or so those torque. We have to plot those parameters for the modeling. And the second part is called the motor modeling. Third part is the engine, typically not for the EV, but for the plug-in hybrid electric vehicle or hybrid electric vehicle, where we need the engine mass, then the tank, then the initial fuel mass, engine block mass, then the engine idle speed, then fuel density, fuel like the LHV, then engine displacement, number of cylinder, stroke, diameter, engine, compression ratio, all those parameters when it comes to this engine modeling. Even fuel mass, then the fuel ratio, then the speed index for NOx, mass, then the speed index, then torque index, and particular mass flow rate. So I don't want to go into those detailed parameters, but these are the typical important parameters required when it comes to the engine part. Then gearbox is also one of the important, whether sun gear or the other type of gear. Then the ring gear, so the number of teeth in sun gear, number of teeth in the ring gear, then the sun, then the initial speed, planet gear, mass, then the blending speed, number of planet gear, speed index, then the maximum efficiency. So all these parameters required when it comes to the gearbox. Then we also need this torque converter parameter like the engine idle speed, then the torque converter mass, the impeller mass, pump mass, speed ratio for torque map, pump loss, slip ratio, then coefficient for index mass, then the torque index, pump efficiency, torque pump torque loss mapping, and so that is something related to the torque coupling. When it comes to DC-DC converter, we need the efficiency, voltage output, as well as the unit mass also. In addition to that, we need the wheel, means the vehicle type, number of wheels, whether it is 4-wheel, 8-wheel, or like that one. Then the maximum braking torque, then wheel radius, single wheel mass, then the zero first order coefficient, rolling resistance, then the first order, second order, third order polynomial part. Then when it comes to vehicle, we need the vehicle mass, vehicle base, CG, height, then the fraction weight on the front axle, rear axle, cargo mass, zero order, first order, second order, and we typically consider the 5 passengers. So for vehicle mass, so 5 passenger, typically we take almost average 80 kg per person. And in addition to that, we also need the brake parameters. So like the upper limit state of charge for charging, then the charging allow SOC, then the motor speed, then the zero deceleration, the acceleration, time constant for the regenerative braking, then internal gain constant for the engine, proportional gain constant, then maximum vehicle acceleration, minimum vehicle acceleration, also an intermediate part. And final drive, basically drive ratio, then the inertia for final drive, mass, then speed, then torque index, speed index, final drive efficiency, torque index, speed index for the drive loss map, and the maximum efficiency for the final drive. And then last part is about the controller. So the lower SOC, then engine on, engine off, time delay for engine on, engine off, SOC threshold, then minimum time, proportional gain, then internal gain, then SOC charge, SOC at max charging, discharging, then percentage, and battery max charging, discharging power at SOC target point. So these are, you can see this one, even I've skipped a couple of parameters also. So we need almost 300 to 400 parameters when it comes to this control, this electric vehicle modeling. After that, the validation. So if you look at this drive cycle, so vehicle speed versus mass. So Toronto to Niagara Falls drive cycle, where so 0 to like the almost this here and 8,000 parts. So here, this is the end of this one. So almost 2 hours and 16-minute one. And then here you can see the vehicles was driven for maximum speed of 125 kilometer per hour. And so this is vehicle speed versus time. Corresponding electric motor power input and motor output power validation. And here you can see the state of charge. So starting state of charge was 100%, ending SOC was 0% with 8,000 seconds. So here you can see 2 hours and something. And so experimental one is basically the red one, and the blue color one here you can see is the model one and experimental. The model one has the smooth line, but if you look at the experimental part, it has those ups and downs, ups and downs, ups and downs. These ups and downs are related to the regenerative braking system. So if you look at this region between 1500 to 3000 seconds, there is no, so here you don't see any ups and downs. So, and all 3 battery packs were continuously delivering energy, and vehicle was driven on highway on the Queen Elizabeth Way with maximum speed of 125. So that is why you can see over here. But after that, there was heavy traffic on towards Niagara Falls. So once we reach it towards Niagara Falls, so here you can see so many ups and downs, stop, go, stop, go, stop, go. And that is related to these ups and downs. So initial model when developed, we did not consider this, the regenerative braking system, but later model was refined, and then we consider those regenerative braking systems. So that is why you can see those ups and downs. And again, total energy was calculated by using this equation, and model versus experimental part is provided. So model has like 15 kilowatt hour versus experimental part, that is 14.3 kilowatt hour. So this is the longest recorded drive cycle validation in terms of state of charge, motor input power, and motor output power. Similar drive cycle was generated like the test drive cycle in the Waterloo city. So this is something about the city and the highway driving. So here you can see start from University of Waterloo and Waterloo driving, and then after then we drove in the highway also, like called the 401 highway, and connecting Toronto to Detroit, and then we came back again, and corresponding motor input power, electrical motor output power validation, and corresponding state of charge is provided over here. So here you can see the validation part. And the vehicle was driven for almost 2500 seconds. So 3600 is almost 1 hour. And here you can see the acceleration validation model versus experiment. And here you can see the efficiency 91% for model versus 90% for experimental part. After that, degradation was also the part of this project in state of health. And then for this particular vehicle, so like the typically polarization curve, so fitting cubic polynomial curve. So like the October drive cycle versus like November drive cycle in 2011 is provided over here. So this is first drive cycle versus second drive cycle. So polarization curve here shows that how the battery voltage and current are changing during the charging as well as the discharging event. And from this typical curve, you can see the voltage versus the current for two selected trips. Estimation of the internal resistance of the battery can be obtained, and internal resistance is the parameter that is directly represents the power fade inside the battery. And it is expected that after sufficient large time period, polarization curve drop will like slope will change, and like it show growth in the internal resistance of the battery. And for the purpose of demonstration here, you can see like the two drive cycles like 106 kilometer versus the 19 kilometer length has been used to generate the polarization curve by making a scatter plot for voltage versus current and the fitting polynomial curve. Again, in this figure, you can see the battery internal resistance is also strongly dependent on the operating temperature, and thus it enables to compare the battery polarization curve that yields an indication of power fade, and the test data should be collected from the trips and basically for the power fade. And again, identical battery operating temperature like dynamometer testing in controlled environment is much preferred for this trip. So again, these two drive cycles were chosen in order to investigate how the battery internal resistance has changed over the 1 year period. And again, when this drive cycle was collected, it was around like the 20 to 25 degrees C temperature. I think someone has to mute, please. So this is about the model, and then it comes to the degradation model. So for power as well as the capacity fed over 25,000 kilometers. So we measure the power and capacity fed for this vehicle over 25,000 kilometers. And for that, NINGS model, extended NINGS model has been selected for modeling this degradation. So here you can see state of health versus trip distance for like the different drive cycles. So USO6, then UDD is known as the urban dynamometer driving schedule. HWFET is the highway fuel economy, and then electric vehicle. So this Burlington Hydro EV and corresponding power fed and over 25,000 kilometer again for USO6, UDDS, and HWFET and Burlington Hydro is provided over here. So as I said, extended NINGS model was selected for vehicle powertrain application, and it takes into account the degradation under constant voltage charging operation. So this model typically incorporates porous electrode theory, concentration solution theory, Ohm's law, intercalation and de-intercalation kinetics. So basically physics-based electrochemical model and transport phenomena in the solid phase and electrolyte phase. So it's typically like the electrochemical part. And based on extended Nernst model, the degradation block was created for this one and in the PCET model, and also voltage state of charge calculation were modified to include the model degradation effect in terms of capacity fed, SOC and power fed affect the voltage. So this particular vehicle, if you look at this table, I think someone has to mute, please. Good. So drive cycles here you can see USO6, UDDS, HWFET, and then this electric vehicle. So distance 15, 12, 16, and then 19, and then kilowatt hour. So 3.8 to 3.6, and then average speed 123 to 55 kilometer per hour. So as expected, USO6 drive cycle causes highest degradation effect, and HWFET has least effect, and Burlington drive cycle has the degradation effect similar to that of the USO6 also. So this is about the capacity and the power fed. And then again, the degradation model validation here, you can see the HWFET, SOC, UDDS, so state of charge versus trip distance. So SOC shows over 25,000 kilometer testing drive cycle, and then this plot shows that the battery ages, as battery ages, it undergoes higher SOC change and larger energy discharge per unit of the distance traveled. Again, vehicle experiences least SOC swing under HWFET cycle and most under the Burlington drive cycle. So we use this model for several drive cycles also. And after that, what we did is this vehicle has the cylindrical cells. So we took these cells, and so instead of like real world driving, what we did, we scaled down this battery pack into cell level, and I can see here Sujina Webex got disconnected by itself. Am I still there, guys? Hello.
Okay, sir.
Okay, that's good. Okay, perfect. So since this vehicle has the electric, sorry, it's 18650, we scale down this vehicle from cell to from pack to cell, and then we did the cell testing inside the lab. And so basically we use the same drive cycle, so real world drive cycle fed into this testing, and here you can see the power input from drive cycle and output from the test bench. So free air convection has been used for this one, and ambient temperature was 22 degree, and Burlington high was 5 degree, and then EV has thermal control. So actually this electric vehicle has thermal controller. So if temperature goes beyond 38 degrees C, then it basically starts all parameter. We also generated Thevenin-based HPPC called hybrid pulse power characterization equivalent circuit model, where battery voltage is calculated by open circuit voltage and the ohmic resistance, and then the capacitance, and then the resistance element, where R0, R1, and C parameter were selected from this paper, and then we measure those part, and then we did those experiments. And here, so from 100% SOC all the way to 0% SOC, we measure R0, R means R1, R2, and the C parameter, which you can see over here. And now, so this is the HPPC data. So I don't know if you're aware about the hybrid pulse power characterization test. So this is the setup. We have a biologic setup, and we use for the HPPC. So here you can see the 1C discharge model, 1C discharge experiment validation, 1C charge model versus experimental. Same way at lower C by 2 charge model versus experimental, and C by 2 discharge model versus experimental comparison. After that, as we collected several drive cycles, we validated those drive cycles. So this is the typical drive cycle, green color one is number 1 drive cycle, which has the highway driving and the city driving. Corresponding voltage validation and state of charge validation is over here. Drive cycle number 2 is typically city driving, which you can see over here, and corresponding voltage validation and state of charge validation is there. Then in color one is drive cycle number 3, is basically the city driving as well as the highway driving, and corresponding voltage validation and state of charge validation is provided over here. Cycle number 4 is the orange color one, is the city driving. Again, back to city driving, corresponding voltage and the SOC validation. So the model worked perfectly for this type of Thevenin based part, and then we validated those ones. When we did this battery degradation capacity fed, so as I mentioned earlier, this drive cycle 4. So drive cycle 1 is basically 63 minutes, second drive cycle is 98 minutes, then third drive cycle is 43 minutes, and fourth drive cycle is 64, means 1 hour drive cycle. Corresponding SOC, ending SOC, starting, all these provided here. And here you can see the outside temperature was +2, then 23 degree, -6, and then 10. So we purposefully collected different drive cycles in order to see the behavioral of the battery and battery pack. And here you can see over 3 months, so July, August, and September. So excluding weekend, so Monday to Friday. So excluding weekend, we selected one drive cycle and we repeated the same drive cycle. So Waterloo to city and then the highway and come back. And then we did the capacity fed measurement, which is quite high, but this is what we got from the vehicle. So it is around 4% capacity fed over the 4 months of the driving continuously over 3 months. So this is about the battery degradation capacity fed experimental side. And after, if you are interested in the machine learning, I will take guys only 5-10 minutes. Let me finish this part because it is little important. So Liebenberg-Marquardt means neural network machine learning model has been used. So machine learning model is typically like, neural network is used to model the complex relation between the input and output data using relatively simple construction and algorithm. So data is presented at the input layer. So here you can see the input layer. So inputs are number 1, 2, and 3, which travels through the hidden layer. So here you can see the H is basically the hidden layer 1 to 12, and weighted connections. So input weight and then the layer weight, IW and LW, and output part is provided over here. So which represents the output of the network. Typical inputs we consider are like the temperature, means the ambient temperature, let's say air cooling and the water cooling. Our discharge rates we selected 1C to the 4C, and battery amp hour capacity. Then MATLAB consider three types of algorithm like Liebenberg-Marquardt method, Bayesian regularization, and scale conjugate. My PhD was on Liebenberg-Marquardt method because, and this is default algorithm in MATLAB because it is a more memory and the less computational times. Now, by the way, for this machine learning neural network based model, we use almost like the 117,000 samples, and out of that 70% means 82,000 were selected for training, 15% for validation, and 15% were used for testing the model. In continuation of machine learning part, again, as I said, three input, then the output layer, and then the hidden layer with weight and bias, and output layer. So hidden layer were varied from 1 to 12, and then once we have like the mean square error of, let's say, the 0.49 at an epoch of 318. At 318, we got the best validation performance and that is our mean square error. Here you can see the training, validation, testing, and the best part. So mean square error is basically all data set on a logarithmic scale as a function of epoch. So error histogram is also provided. So here you can see the yellow color line with 20 beans. So error histogram is basically target versus output, and majority of the error lies in a range of -0.3 to +0.52, and this plot provides the regression plot actually with the R value of 0.99. So R is equal to 1 means close relationship between input as well as for the output. So this is a neural network base, and here is the validation part. So again, 5 degree, 15 degree boundary condition, 25 and 35 degree, and validation of the temperature. So experimental versus validation part, and you can see good match. Level of model is basically able to track profiles observed in the experimental results, and strong agreement between experimental and modeling results demonstrate the robustness and accuracy of the model. Similar validation is at the 4C discharge at 5 degree, 15 degree, 25 and 35 degree, and surface temperature is higher at higher temperature and lower at the lower. And trend observed is actually increased discharge rate results in increased surface temperature at all thermocouple locations. Then voltage validation part, same way for the machine learning part, 5 degree, 15 degree, 25 and then the 35 degree. And so again, there is good agreement between experimental and simulated data for voltage distribution at lower C rates. Again, voltage validation, so actual versus simulated for 5 degree, 25, 15, 25 and 35 degree. And here you can see the initial sudden drop of the voltage, and that is possible because or that is there only because of the cold climate condition, because of the so outside temperature was 5 degree, but quickly recover in the voltage is possible because of the increase in internal resistance of the battery, which increase the battery cell temperature, that leads to the enhanced performance. And the trend observed is again increase C rate, decrease operating temperature results in decrease discharge amp hour capacity of the battery. So this is about the model validation, and then we develop the mathematical functions for neural network with the input and the hidden layer. So basically, T is the time, theta is the charge discharge amp hour capacity, and zeta is the boundary conditions, and then corresponding tan sigmoidal function is provided over here. And the expected drive cycles from this vehicle so basically was used to validate the model, and here you can see the validation. So at later part it is matching perfectly when it comes to this real world drive cycle. And then weight matrix connecting the input layer with the hidden layer are provided over here. So basically weight and the bias, and then clean. So those who are in mathematical side, they might know about this mathematical function. So bias values are provided for this one here provided, and then like lambda function obtained for the output neuron with the Perlin, and that is in the linear transfer function in the MATLAB. The weight matrix connecting the hidden layer neurons with a single output neuron, and weight matrix are provided, and bias associated with the typical output neuron is provided over here, that is minus 0.29, 0.29. This is probably end of my presentation for this mathematical functioning and then these neural network side, and interesting papers are also provided over here. Thanks for your attention, and I've used these many references for today's presentation. Thank you so much for your attention, and I'm here for another 20 minutes for your all question answers. So thank you so much. So guys, I'm here for another 20 minutes, so we can start the question answer.
Hello.
Yeah, go ahead.
There are almost 400 different parameters that one has to consider in modeling various subsystems of the EV aspects, EV. While aiming at coming at reliable results, what are the preferred values or set of parameters that one chooses for modeling? Any experience based and guidelines?
So again, it depends on vehicle to vehicle. Plus, it depends on the type of battery. But if you are talking typically about the Ford company, they are using this cylindrical vehicle for this battery. So if you have a similar battery in different vehicle, let's say Hyundai, if you have similar 18650 with almost same, you can use those cell parameters called ESS, called energy storage system parameter. But vehicle mass and little, you have to modify those little parameters for based on the vehicle dimension, mass, and couple of other stuff. But yes, if you have same vehicle, if you have a different vehicle with the same battery, you can use couple of parameters based on my published paper. And again, typical parameters for vehicle modeling are the energy storage system, power, means the motor, and the controller, and vehicle dynamics.
Okay, thank you, sir.
Yeah.
Hello, sir. There are several questions in a chat box. Should I read it for you?
Yes, please.
So the one question from Venkatesh is PSAT and autonomy softwares are open source.
No, it is very expensive. At that time, before 15 years, in 2010, yes, almost we paid $25,000. So right now, probably it is expensive. I don't know right now, but inquire. So this software is developed by, you might know ANL, called Argonne National Laboratory. That is in Chicago. So Argonne National Laboratory developed this autonomy software. But again, the background files are the MATLAB, okay? So if you have a MATLAB Simulink or MATLAB in your laptop, you can use couple of stuff on that one.
Sir, second question we are having, that is when we mean hybrid, do it mean only the fuel and electric or hydrogen or CNG?
No, right now I am talking only about this hybrid electric vehicle, means it's only the engine plus battery, okay?
Okay, and in addition to that, the same question, what hybrid power you have used in your model? Will the size of hybrid will be larger than pure electric?
Yes. Because the hybrid had like the smaller battery pack, very small battery pack. But main focus was on the first Canadian electric vehicle. So electric vehicle was the main focus for the study.
So one more question is there. How do you set the parameter values while modeling? Are they empirical, measured, or should comply with any data sheet?
No, they were measured parameters. Majority 60%, 70% parameters were measured, and remaining 30% parameter we did it from we collected from literature review.
What is the preferred set of parameter for various subsystems? I think this question you might have answered.
So preferred set of
It is answered.
Okay, sir. So I'm moving to the next question. What is the difference between cylindrical and large batteries, and which is preferred?
Cylindrical batteries have smaller amp hour capacity. So as you can see in this slide, it's only like the 1.5 amp hour battery. Okay, so it's 1.5 amp hour. So you need more batteries, so around 6,000 cells. But if you want like the bigger battery pack, like if you need the higher energy density and stuff, then you have to go for the prismatic battery, and you have to take out the engine and put this battery pack. Typical, again, it's a good question. If the best example for cylindrical versus other batteries are Tesla. Tesla is the only one using this cylindrical battery. Still, they are using cylindrical battery, and other OEMs, General Motor, Ford Motor, Hyundai, they are using this prismatic pouch battery. So typically, basically, they take out the engine and they put the battery pack.
Can I ask one question, sir?
Sure.
Generally, it is revealed that liquid cooling is better than air cooling.
Yeah, but that is for larger battery, not for the cylindrical battery.
In spite of that, only company, perhaps the only known company using air cooling is Tesla, compared to many other who are using water cooling, liquid cooling in electric vehicles. In spite of that, what is the reason that Tesla is number one?
Yeah, so that is that monopoly.
Any other aspects, including technical and marketing, that is instrumental for this? Air disadvantage with respect to water.
Okay, so this is a very good question. Why Tesla is successful in EV? So if you look at the video, Tesla has cells like all the way from front to back on the bottom side of the vehicle. When it comes to other OEMs, like again Hyundai, General Motor, Ford Motor, they take out the engine and they put the battery pack. So they have battery pack only at the front side. So that is probably one of the reason for comparison of the battery. Number second, when it comes to air cooling versus passive cooling, so almost all OEMs are using refrigerant base with R134A refrigerant based cooling, while Tesla is using the like the passive air. passive air doesn't have the drawback for the lithium plating. So I don't know whether you are aware about lithium plating, but other vehicles have biggest issue with the lithium plating because cells are placed in vertical position and coolant channels are at the bottom. So cooling is only at the bottom side of the cell, and that is why one of the biggest drawback for water cooling is for the lithium plating, and that is why they are not getting the enough range even during fast charging, because current is more towards the anode side. They have a big problem for the fast charging. So these are the couple of reasons for air cooling versus water cooling, and Tesla versus other OEMs, means cylindrical versus pouch or the prismatic battery.
And this too, in spite of the fact that Tesla vehicle outer profile is not that attractive. To be frank.
Tesla is very successful model in North America, probably not in India, but in US it is one of the successful model.
Yeah, I'm particularly comparing this overall outer shape of EV versus the traditional vehicles. So there it is like a old 60s decade kind of general shape. In spite of that, it is the world's number one. That is why I was just trying to highlight.
Yeah, so it's probably aerodynamic shape because of the range issue. So that is why you will see this, like, you know, the other type of shape in comparison to other vehicles for Tesla model.
Yeah, okay. Thank you. Thank you.
Sir, we are having next question from Dr. Arti. She is asking, is neural network algorithm giving better results than other optimization algorithms for thermal model?
Yes, you are right. So in one of the paper, so in first paper I use Liebenberg mark plot, but in remaining two I use the Bayesian regularization and then scale conjugate and couple of other methods also. Even we compare the like the different method and then de-optimize. So which method is the best one? So go to my Google Scholar profile and you will find that compare optimization method algorithm paper for this particular battery. And Aarti, if you are working on this modeling side, and if you need my data, I will be happy to provide raw data for the vehicle.
Sir, I'm interested in thermal management. I'm taking
Sure.
I have just now I completed my PhD in battery charging algorithm by solar MPPT techniques. So
Okay.
I have interest in that. So I need to know whether a neural network is really helpful, is giving a better performance than the optimization algorithm.
Yes,
So
yes.
any
Neural network is.
are using optimization algorithm. That's why I have keen interest. So is this algorithm is very useful to get the good performance?
Yes, yes, you are right on that one. Send me an email, Aarti, and I will chat with you also.
Okay, sir. Okay.
Okay.
So I'll give the
I
email.
will even give me your Gmail ID later via email, and I will share my lab data, and you can have some access to the data also.
Okay, sir.
Okay. Yeah.
Thank you, sir. Thank you. Thank you so much, sir.
So next question we are having from Mr. Sandeep. He is asking, apart from design of electrical systems, was there any mechanical fabrication of vehicle chassis or use of advanced manufacturing 3D printing involved in retrofitting of old IC four-wheelers?
No, I don't think I have worked in that area. To be honest, I haven't worked on that 3D printing or then old way or those type that no, never. Sorry.
Hello, sir.
Yeah, hi.
Sir, I'm want to ask question regarding the recycling of the battery because now people more government even people more over talking regarding the battery usage of battery. Last month I visited my BTech student to a recycling plant, Gravita. They were basically dealing with the plastic recycling, aluminum recycling, and battery recycling. Lithium ion, not lithium ion, or client battery. So, is there any plan of by the any government in the world for the recycling? Because so it at the present is the initial phase of usage of battery. As it will grow, as the market will grow of EV, the recycle will be an issue. I think, especially for lithium ion battery.
Okay, sure. So very good question. So the secondary use of the battery basically means the recycling of the battery is again hot topic right now, even in North America as well as in the India. So if you are interested in the secondary use of the battery, my professor is working on that area. I'm not working on secondary use of the battery, but uh, according to my point of view, that is also one of the hot topic when it comes to this lithium ion. So basically collect those batteries if you are in Pune region, so collect those batteries, and at least collection of the battery is also one of the task. And after that, connect one of the plant, and then you can extract the remaining, the lithium, and they can use the lithium for the other batteries also. So there are two tasks. First one is the find out the collection of the battery, and then reuse that lithium, or you have to do your own plant for lithium extraction. I have no idea on that one, but that is one of the hot topic right now in India.
Okay, thank you, sir.
Hello.
Yeah.
Sir, one more, I think
Sir, I will like to add here a little bit. In the last week, I have met one of the person who they are utilizing the French technique to recycle the lead acid batteries, which will going to give the instead of 100% efficiency, they are provided 80 to 70 to 80% efficiency. So, can you put some light on this topic?
But you are talking about lead acid battery.
They are recycling lead acid battery, and they develop their own machine.
But that is with the water. So lead acid battery is typically only 12-volt system. Typically we use for start and stop of the vehicle, radio, wiper, electrical accessories. We use that for the smaller application. So less than 12 volt.
Yes.
But if you're talking about the vehicle driving, we cannot use that lead acid battery for vehicle driving. We have to have lithium ion battery, which has higher energy density and specific energy.
Yes, that is okay. Just I am thinking from recycling point of view, because I have learned that French technology is developed. I am not able to get it, but if you are knowing anything, then I will like to connect with you also on this.
Good question. To be honest, I haven't worked on 12 volt
Okay.
battery.
No. That is a recycling of lead acid battery.
Yeah.
They have started in India now. Now they will want to develop again in another battery. So one is started. Day after as month is passing, we are going to get reach up to lithium also, na? That's why I will want. This is the one of the emerging area where we can send our students.
Yeah. So just since you raised this point, 5 hot topics for industry or even in the for battery are: first one is the secondary use of battery, means recycling. Second one is the thermal runaway, means puncture of the battery. Third one is the thermal management. Fourth one is the aging, and fifth one is the like the fast charging. So fast charging is one of the hot topic right now for the battery.
Thank you, sir.
Yeah, very good question. And
Thank you,
I'm glad that you are thinking on the secondary use of the battery.
Yes, sir.
Okay.
Yes, sir. Thank you, sir. Thank you very much.
Next, please.
Instead of concentrating on EV to minimize CO2 pollution with so much investment, why we are concentrating on planting trees with minimal investment?
Come on, this is grade 8 question. We all know that. Gas price is high, so we need a alternative for this electric vehicle, and lithium ion is only one solution right now. So if you find another solution, then that will be great. We will be the new one. Okay. Let us go to the next question.
Sir, I think all questions are over. If any participant is having any question, you can unmute and ask.
Good evening. Hello.
Yeah, hi.
We have talked a lot about research about the battery, sir. Can you tell me some details about the maintenance of the battery of an EV? Maybe two-wheeler or four-wheeler?
So typically, two-wheeler, I have no idea because I left India before 20 years. So I'm a Canadian citizen, and I have no idea even much about the Indian market. But when it comes to this this maintenance part, yes, typically for four-wheeler, when we design the battery pack, the maintenance cost is almost after 10 years. Okay, so after 10 years you have to replace the battery pack. That cost is very high, around 10 to $12,000, so almost 6 to 8 lakh rupees. So this is the typical cost for the maintenance cost of the battery, means the replacement cost of the battery. Maintenance wise,
I'm talking about while running the vehicle, we have already some technology to monitor the battery. Other than that, as a human or as a owner of the vehicle, what things he has to take care on the battery physically?
So BMS, cell to cell variation. So let's say if you have a 300 cells, bigger cells, or 6,000 cylindrical cells, you have to have good BMS system in order to get correct voltage from all batteries. So let's say out of 6,000 cylindrical cells, let's say your 200 cells are not working in one of the module, then how will you know that one? So those type of hurdles are big issues right now. So cell to cell variation means voltage variation is one of the big part when it comes to this question.
Okay, sir. If you want to actually know the practical problems in the battery maintenance, so from where can you get it? Can you get it from you, mail or something?
No, I cannot keep quiet. I
Okay,
don't have
thank you,
much.
sir. Okay, fine.
Sir, next question we are having from Ritesh. Sir, can MATLAB be used as a simple tool to begin and understand modeling of EV, specifically about the battery management system, or is there
Yes.
any other tool?
No. MATLAB is the best tool for EV modeling, even battery modeling and BMS modeling also. Ritesh, there are a couple of tools, or even look at my Google Scholar profile and you will find those papers also on MATLAB, even MATLAB Simulink also.
So, is there any question from any of the participant? Okay.
Thanks for a very nice presentation and quite informative, and obviously it triggers the further thought process. But if possible, we will request you to share the presentation, because this will definitely be needed for completing the absorption in our for the comprehension further and reference.
Yeah, I've already uploaded my presentation in PDF to Google Drive, which I received from Professor Sagar Wankhede. So he will distribute to everyone.
Okay, thank you. Varsha madam?
Yes, sir. Yes, sir.
The feedback link is common for both sessions.
Yes, sir. Yes, sir. You have to fill only one feedback form.
Thank you, madam. Thank you.
Okay, sir.
Thanks for very informative and deeper and
Good luck.
broader presentation.
Sir.
It has definitely triggered further interest.
Sure.
Thank you, sir.
Yeah, good luck. Good luck.
Satyam sir, I have one question.
Sure.
So you have shown most of these slides, and in most of these slides, in battery cooling, you have used different coolants, but I found nowhere you have mentioned about the nanofluids. So is there any work going on in nanofluids from your side?
No, I'm not.
Battery cooling.
So you are you talking about the like the PCM, CNT and those stuff, carbon nanotube?
Carbon nanotubes or aluminum oxide particles.
I haven't used. I have my colleague who is using this CNT, PCM, and different combinations. I haven't worked on that one, but I do have the data for that PCM and then carbon nanotube part. So if you need, I can definitely provide that data.
Yes, sir. Okay.
Okay. Yeah.
Thank you, sir.
This is Dr. S. J. Actually, upcoming research areas in this field, can you give one or two in that?
Sorry. You were
Research
disconnected.
areas. For example, a new person is want to do some research work in this area, electrical vehicle, battery management system. In which area he can proceed his work?
Thermal runaway. That is hot topic. Very hot topic. thermal runaway and the BMS and machine learning.
Thank you, sir. Thank you. Thank you.
Okay, and even fast charging.
So I think participants are done asking the questions. So I would like to propose the vote of thanks. So on behalf of PCCOE Pune, I extend my heartfelt gratitude to Dr. Satyam for sharing his profound knowledge and the research insights on advancing battery thermal management for fast charging. And he also shared various modeling methods, and I believe your vast research findings and topic expertise have truly enriched the participants' understanding of these critical topics. Once again, I thank Dr. Satyam for his valuable time and contribution to this ATAL FDP. I also wish to express my sincere thanks to all the participants for joining the session and participating actively. With this, I would like to close today's session. See you, all of you, tomorrow. Till then, goodbye and happy Christmas Eve to everyone.
Bye. Thank you, guys. Thank you for attending. Have a nice day.
Thank you, and
Thank you, sir.
Hello, Varsa,
best
ma'am.
wishes for the festivities.
Hello, Varsa, ma'am.
Thank you, sir.
So far, we haven't get any slide, ma'am, of any session. So please share the slide.
Yes, sir. From the coordinator side, the Google Drive link will be shared either today or by tomorrow itself.
Okay, thank you, ma'am.
Okay. Okay.
Thank you so much, sir.
Or in feedback form, it is showing only session 5, not session 6.
Madam, organizer, madam.
In feedback form, it is showing only session
We have
5
only
regarding
one
time.
feedback form, sir, because speaker is same for both the sessions, so we have sent one feedback form only.
So the
Feel that
topic
one
we are
feedback
asking
form
only
is
the 5,
applicable
not
for
regarding
both.
the 6th session.
No, the form is same for both the session as speaker is same. So we have designed only one Google form, feedback form. So you can fill that form that will be considered for 5th and 6th session, both
Okay.
sessions.
Okay, thank you.
Yesterday I have filled feedback form. Will it be considered, sir, for today's session also?
For today's session, so we have same speaker for both the sessions. So we are going to consider the feedback for both the session. Means if you are filling this, you are supposed to fill one feedback, and that will be considered for both the sessions.
Okay, sir. Okay. Thank you, sir.
Hello, sir. Mr. Sagar, sir. Dr. Sagar, sir. Hello. Dr. Sagar, sir.
We are writing the
Sagar, sir.
topic name only 5th in a feedback form because you are asking for a 5th session.
Okay, no issue, sir. No issue. You can give
thank you.
directly feedback. So we are going to consider it for 5th and 6th session, both.
Okay, thank you.
Dr. Sagar, sir. Hello.
Hello.
Dr. Sagar, sir.
Hello. Yes.
Organizer, sir. Hello. Organizer ji.
Hello.
Sir, actually, sir, really the presentations are very good. Unfortunately, because of online, sometimes we are not able to continue with the presentation. If you have the video links, that will be very good, sir, really.
Okay. We are going to share you all the links and all the PPTs by 30th December because we are going to finish this FTP by 28th. Most probably, we are going to send all the PPTs, all the videos to your through Drive link.
Okay, fine, sir. So that means we will be sharing after ending of the
After
after
completion
finishing
of
of this season.
FTP, this FTP.
Okay, thank you, sir. Okay, thank you. Continue, sir.
तमिलनाडु में पता हमारी पार्टी बीएम के भारत में मोदी बजट को आपका तैयार था पीएम के घर के जो
So we are going to wait for next 5 minutes. So please fill your feedback form immediately.
सर transfer